The other day we talked about the allegory of the cave and the AR goggles that represent the phasor diagram that we use to describe in the complex plane that we use to describe the very real physical response of an RLC circuit. And we took that sort of analogy out of the context of the discussion we had back in Physics 231 of oscillation. We said that a mass oscillating back and forth at the end of an ideal spring is describable as the projection onto one dimension of two-dimensional rotational motion. A cosine omega t. As long as A has to do with the maximum displacement from the equilibrium position of the thing. Here we're assuming that the equilibrium position is at the origin. And as long as omega is actually related to the physical parameters, as long as we've got the goggles set to the right setting, according to the stiffness of the spring and the mass that's oscillating at the end of it, the angular frequency of the settings in our goggles mean that as that thing moves in a circle, we have perfect alignment with the actual object moving back and forth in one dimension in the real world. Suppose we have a mass-loaded spring that we have contrived to oscillate in simple harmonic motion, let's say vertically, and we have a string attached to it that the left end of the string moves as the mass moves. This disturbance propagates along the string. And if it remains periodic, we can call it a wave. Remember from your discussion back in what? Pre-calculus? When we talk about sinusoidal functions, that we can talk about the crests and the troughs of a sinusoidal function like this. And we can talk about the amplitude, and that's no surprise. You've been talking about that. Remember that for a physical wave moving, a periodic disturbance that transfers energy from one spot to another, because that's what happens, right? The actual mass of the string far away from the mass that's oscillating on the spring, that string has mass and that mass moves, which means it has kinetic energy that it didn't have before. And the only reason it has kinetic energy is that we sent it there using this wave propagating along the string. All right. So we're sending this periodic disturbance along the string. Now, this is a thing, a phenomenon that happens in space and time. It's true that the vertical oscillation of that suspended mass is a function only of time because, well, it's not moving in space. I mean, it is where it is. I mean, yeah, it's moving up and down, but its vertical position is only a function of time, not of where it is. But as we watch that disturbance propagate along the string, the state of the string at any given location is an individual function of time. But the statement of what actually happens is a statement both of position along the string in order to talk about what a piece of the string is doing at any particular time. We also need to know where along the string we are. Through space, got to go from one spot to another. Otherwise, it's not a wave. We just have an oscillation, which is no bad thing. But we have some periodic thing that we're is going to sort of initiate the transmission of energy from one spot to another in space. We'll call that a wave. Now, how many kinds of waves are there? You might have encountered this when you were doing 231 in the first place. Different professors treat waves at different times. I know that when I teach 231, I try at the end to say something about waves just to sort of set folks up for, but a lot of the time it's saved because we don't really need it until now. So it's true, there are two kinds of waves. The kind in the picture is transverse. We propagate away from that oscillating mass on the spring horizontally, but the individual pieces of the string are moving vertically in sort of parallel with the vertically moving oscillating mass. The disturbance itself is sent horizontally perpendicular to the oscillation direction. So we're moving the medium across like transit, across the direction of propagation, transverse. So the other kind then, not perpendicular, but those are ditto marks. The motion of medium is now parallel to. So, okay, so what does that look like? I'm so glad you asked. Gosh, I wish I had a slinky or some sort of spring-like thing to use to demonstrate such a phenomenon. This is going to be hard to see. If I collect some of the slinky here, and then, does that help any? Well, I guess we want to be closer, but then it's going to be really hard to see. What if I'm way back here? No, then we're not going to be able to see. But all right. If I release this clumped up stuff over here, it's going to push against the slinky next to it, which is going to push against the slinky next to it and next to it, next to it. And that sort of pushing is going to propagate along the slinky in the direction that I have stretched it. But the motion of the slinky itself is along that direction as well, which is different from this kind of motion. This is transverse. How many pieces of information do you need to fully describe a wave? Five parameters we need to fully describe a wave. How do we talk about them? One of them is shown in the figure from the textbook that I just presented. We've got our mass on the spring, and we have the string attached to it. And it shows us a sinusoidal disturbance. And what it shows us is a photo, just a snapshot, an instant in time of the shape of the propagation through space. The horizontal axis here is space. From this picture, we can measure the amplitude, and the distance between successive maxima, minima, corresponding points on the wave. The amount of space that it takes this periodic disturbance to repeat. What is the period in space, the spatial period of this phenomenon? Suppose we wrote that with the Greek letter lambda. When we call it a period, I think about the sinusoidal function that represents this picture. And I think about it in terms of its argument. And I think about the four parameters that adjust the picture of a sinusoidal function on your like cathode ray tube screen. The period is, we're talking about the horizontal scale of the picture on your old school computer monitor. And that's the coefficient. Let's see, that's well, actually, as labeled, this is cosine something. Question mark x. This has an amplitude a and a cosine function, and the coefficient is the coefficient of x inside the argument of this function determines the period, right? 2 pi over question mark should be the period. That's how the sinusoidal functions worked. And we know that the spatial period is lambda. So question mark then is 2 pi divided by lambda. So this makes me think a lot about 2 pi over omega is equal to the period, or omega is 2 pi over the time period, the temporal period. So this stuff here is a spatial question, spatial statement. This was angular frequency. So this is angular spacing? Capital T was the temporal period, and then we talked about it as 1 over f, which is, and we said that omega is the angular 2 pi radians frequency. So I guess, I mean, I feel like there's something we could define here. This is like 2 pi other question mark. I'll use an exclamation point. This isn't 2 pi factorial. It's 2 pi something. Where that something is like not how many cycles per second, but how many cycles per meter. It's like it's a spatial frequency. How many things per unit length, per unit space, as opposed to how many things per unit time. Okay. The terrible name we give for this phenomenon is wave number. What the, no, it's the angular spacing. We've made it an angle by talking about 2 pi. So we've converted the spatial frequency into a radian value so that we can feed it to cosine. That's it. That's all we're doing. We call that wave number. I have no idea how fast, if this is all the information I have none of this information. I don't have a temporal picture. I have a snapshot. I have one instant. If what I want is temporal time domain information, what I need is a video. But I want it of one spot. This whole diagram on the left holds time constant. Something, some value of time. Snapshot. This picture on the right is going to be evaluated at some fixed position. And we have some sort of sinusoidal function there as well. From this picture, we could, again, measure the amplitude if we wanted to. But here we could measure the temporal period, how much time per cycle. And as soon as we write capital T, we can fill in all the blanks here. We can talk about omega now. And we can talk about the angular frequency, the straight up frequency cycles per second. Angular frequency, what would you call it? Frequency, I suppose. There are 5 parameters here. I mean, I guess amplitude, K, wave number, lambda, but K and lambda are really the same. Like if we know one of them, we know the other one. we can talk about the period, but I guess if we know the period, we know the frequency. So really, there are only three parameters here: amplitude, space parameter, and time parameter. The other thing I might be interested in is how quickly this disturbance propagates to a distant point. In other words, how fast is the disturbance moving along this string? I need a speed. One cycle. One cycle occurs in a wavelength worth of space. The spatial period divided by the temporal period gets me how far did we go in how much time. So we can, if we have both domains worth of information, we can write down the speed with which this wave is propagating. I guess that's only four. Only four parameters really, or six depending how you count. Can we put together a complete description all in one statement? Well, one mathematical relationship that talks about a propagating disturbance through space? Suppose at time zero, the mass oscillating on that spring that's starting this whole train rolling has, a particular y value. That y value is going to be carried along the string. And that y value is going to propagate along the string a distance in an amount of time according to how fast we're going. In other words, we can take our original statement if we want to know at what time we get to coordinate x. Well, it depends how fast, like we're traveling with a speed v, which means that it takes time t to get to position x. So if we're interested in what's going on at coordinate x, we need to ask about what was going on at the source that much time ago. But as time goes on, we just keep needing to take what time it is and subtract the time that it took to get to the point where we're interested. So it's not just t, but what time is it now, and how much time did we spend getting from the source to here? Because that's how far we have to look backwards to get the current value of the function.
The equation that t is equal to v over x, did you get that from v is equal to x over t?
I did.
Wouldn't it be x over v?
Yes.
Cool.
Who knows what he'll write? That's good. Keeping me honest. I like it. Cosine is an even function. And in this particular case, I think there's a good reason to switch this for our like sort of intuition, but it's convention. It is the convention that we use to write this. So I'm following the convention in this case. Now, omega divided by the speed of propagation. Omega is the frequency divided by 2 pi. So where we had f, we could replace that with omega over 2 pi. So if we wanted to isolate omega over v, that's 2 pi over lambda. But we've written that once before. 2 pi over lambda is that thing that we called the wave number. We derived it for one particular x value, but we could expand this to include the whole range of x values if we write this as a two-valued function. No, that doesn't make any sense. Not as a two-valued function. That's not a function. As a two-variable, a multivariable function. And now we have a mathematical description of a wave traveling to the right. If we wanted to travel to the left, we're looking the other way in time. Or the other way in space, but cosine is an odd function. Even function. From this description, How do we get back again to the speed v? Well, I mean, we could talk about lambda and f and find the velocity that way. But the speed of the wave is the speed that we would have to travel to keep up with a point on the wave, right? As we're following a crest becoming a zero, becoming a trough, becoming a crest again, if we wanted to keep pace with that, it's like the edge of the disturbance as it's propagating along the string, we would have to travel with the speed that the wave is using. But that means that as we're looking next to us, the phase of the thing that we're following doesn't change. The crest that we are following is still a crest. We're just moving with it, which means something. There is some phase that we're trying to keep pace with. Suppose we take a derivative with respect to time. Because that phase is constant. So when we talk about wave speed, what we really kind of mean is the speed that we need to keep up with the wave, with the phase of the wave. In order to stay in phase with the wave, this is how fast we have to travel. We'd call it the phase speed, if you want. Some consequences. Just write it again. The velocity of each particle along the string at each time is the derivative with respect to time only. The partial of the function y with respect to only time holding x at its value along the thing. Derivative cosine is negative sine, but the negative omega from the argument gets us a positive sine and an omega out front. If we want to talk about acceleration instead, we take another derivative, but it's got to be a partial derivative. Derivative of sine is cosine, gets us a minus sine and the omega out front. But a times cosine of kx minus omega t, that's the original function y. Which doesn't feel all that strange that the acceleration is negative proportional to the position. That's oscillation. That's where we started in the previous chapter of the textbook talking about the motion of a mass on a spring. How did we get to the motion back and forth? It's the simple harmonic motion. It's hardly surprising. Okay. Suppose that instead of partial derivatives with respect to time, we took partial derivatives with respect to x. Negative ka sine kx minus omega t. We take another derivative. Derivative of sine is cosine. We get another factor of k. But here again, that's the original function y of x and t. This has to do with the curvature of the spatial snapshot. The shape as a function of x. The second derivative is the curvature. It's a meaningful thing to do on its own, but then this is the last thing we'll say for the day. Suppose we called this equation 1 and this equation 2, and we divided 1 by 2. Think about that. The second partial with respect to time. Second partial with respect to y, or second partial of y with respect to x. Cancel the negative, cancel the y. Omega over k. Omega over k, though, is v. That's the phase speed, the propagation speed of the wave. So if we cross multiply, this is a really strange way to write this. Hopefully it hopefully it makes some sense. I'm gonna ask you to trust me on this. I know I've been making mistakes all night, but this turns out to be real. The partial if you're following along in Young and Friedman, they write it this way, but in fact, it is the equation that they have written. I stopped writing the y of x and t, but yeah, we should have that in there as well. Otherwise, it doesn't make a whole lot of sense to talk about a partial, but yeah. We call this the wave equation. It has a lot to do, a lot together, tied up together with this idea that simple harmonic motion is expressible as an acceleration that is negative proportional to the displacement. If we allow that disturbance to propagate through space, this is true. Like, we have to have this. If we allow the oscillation to be a disturbance that propagates periodically through space, this has to be true. Just like we did with simple harmonic motion, anytime we can write that the partial of anything is positive proportional to the partial of that same thing with respect to space, smiley face here is a wave because it satisfies the wave equation. Just like we did, if we can say that some quantity is like negative proportional to its own derivative, its own second derivative, excuse me, that is an oscillatory thing. Same story here. If we can show that the second partial with respect to time is positive proportional to the second partial with respect to space, it's a wave. Whatever it is, it's a wave. It's got to be. And this is the square of the phase speed, the propagation speed through space. We're going to need that. An important result.